CMOS analog mixed signal IC design. In today's class, we will be talking about examples of common source amplifier and what are the active loads, and we will look about at least 2 or 3 examples to understand how things are going on. So let's begin with the first example. So in this example, we will see a resistor when it is connected to the gate and the drain. What will be the design spec? How will the design look? V in to the gate, source is connected here. This is the drain connected to VDD. There is RF and RS. This is RD. There is your Vout. So the question is, calculate the gain. Simple question. We will do it really quick. What is the simplest way of doing this? At this node, apply KCL. KCL at output node. What do you get? V out minus V in divided by RF. First one. This branch is over. Next, what is a branch? GMVGS, right? Output node. GM1 times VGS. Then you have an, after GMVGS, you get an R out node. So at the output of R out, you get, what do you get? V out divided by R out. Then you get, at the output, there is drain connected. V out by RD. Correct? Now this total current is equal to 0. Now, how do you simplify? Easiest way, you've got 2 V in terms and 3 V out terms. V in terms, you take it that side. So V out times 1 over RF plus 1 over R0 plus 1 over RD is equal to V in by RF goes that side. So V in minus RF, that becomes plus RF. So 1 plus 1 over RF minus GM1. So what is the gain? Gain AV is V out by V in equal to 1 over RF minus GM over 1 over RF, 1 over R0 plus 1 over RD. So this is the gain. Now, if you have to give this, bring it into the factor of minus GMR0, bring this minus side outside, minus, it will be GM minus 1 over RF times 1 over RF plus 1 over R0 plus 1 over RD. What does this mean? 1 over R effective. So these 3 resistances are in parallel. So GM has a factor of minus RF because of this feedback. Now, this is feedback or feed forward. It can be both, because from input it is going to output, it is linear. Or you can say from output it is coming to input, both. So this will typically be called as a feed forward. So this is a feed forward resistor. Because your input is going to the output, this will help us in getting it. Or you can say the output is being fed back to the input by using RF. So both can be considered. Now, if you do this in our regular op-amp factor, assuming this becomes your op-amp, so this from input to the output, there will be a connectivity. So here RD is connected, or the other way. So it is connected to the supply Vout, and there is input to the output connection. And this is connected to the positive terminal, output is taken negative. Grounded, this is here. Right. So as you are familiar with this structure, this is how you can visualize it with more familiar structures. Okay. So this was example 1. Let us do a second example. Okay. Now, in this case, this is one of my favorite circuits right now. So this has got a lot of industry applications going forward. You would use this in many circuits. This is V in. Here is V out. This is VDD. So what is the question that you will find out? There are 2 ways of finding out this question here. So first part, assume notation is important. So M1, M2. Assume M1 and M2 are in saturation. Right? Find out what is the voltage gain. Find the voltage gain. Second part is assume M1 is in saturation. M2 is in triode. Find the voltage gain. Right? This second question is your assignment 2. Assignment 2. Due on Friday evening. Friday evening, 11:59 PM, you should upload. Okay, this is just one of the assignment problems we will do here. Okay, now let us solve the first one. How do we do the first one? The previous one we did not draw the small signal diagram. Now let us draw here. Just to quick refresh. So what does this look like? Input is given to both here and here. Correct? So important point is GMB, here it is here it is ground. So here VSB equal to 0, VSB not equal to 0. When VSB is not equal to 0, you will have GMB coming into the picture. Here GMB is equal to 0. Okay, so GMB is there, current is the same through both, so ID is same. What is the VGS? V in minus VT, VGS minus VT. Here what is the VGS? This is V in. What is this value here? V out. V out is equal to VDS1, right? So V in, so this is VGS minus VT 1. VGS1 minus VT1 is equal to V in minus VT. VGS2 minus VT2 is equal to V in minus V out minus VT2, right? These are the two. Next, VDS1 is equal to V out. Then VDS2 is equal to VDD minus V out. VGS, VGS2, VDS1, VDS2, ID. ID is given. ID is common to both. ID1 equal to ID2 equal to ID. Right? Now, how do you find out? Simple. Again, you want the gain, right? So you need something with which connecting the input and the output. The simplest one is do KCL at the output node. So what do you get? So you have got two ROUTs. Let's draw a diagram just for benefit. This is M1 RO1, M2 RO2. Right? You have a GMVGS here, GMVGS here. You have GM2, GMB2. This is GM1, no GMB. Okay. So these are the variables that you have to play with. And here VGS is V in minus V out minus VT. Now let's solve. So what is the KCL? First thing you get at this point is you have GM2. GM2 will be GMVGS. GM2 VGS. V in minus V out. Minus VT will give it a side. Plus RO2 by V out going to ground. So minus V out divided by RO2. That is one direction for GM. Now, what will be the other direction? GM V in. GM1 V in 1 plus V out by R out. RO1. Now, how do you simplify? All GMs this side, all V outs that side. So you will get V in is equal to GM2 minus GM1. Then you have V out 1 over R naught 1. This becomes plus 1 over R naught 2 and plus GM2. So AV is equal to V out by V in. How much is V out by V in? V in goes here, this term becomes below. So GM2 minus GM1 over 1 over R out 1 plus 1 over RO2 plus GM2. Right? This is going to be your factor. So clue for your assignment 2 is see what all factors are included and get back here. Okay, find out what is the value. Hint is M2 is in triode, right? So what is the triode equation? Equate the currents equation differently. So the GMVGS you will change. ID factor will get changed. Okay. Next, let us have another practical usage. Example 3. This is one of my favorite interview questions that people ask. PMOS. Okay. For PMOS device is there. For this PMOS device, there is a between the PMOS and the NMOS, there will be a resistor. Now, the fun comes here. This is V in, M1, M2, RD. Where is the V out connected? V out is connected at RD. The first part is this terminal is connected here. There is VD. Okay. Again, we will have the same question. M1 and M2 are in saturation. Assume M1 and M2 are saturation. Calculate the voltage gain. Otherwise, what is it called? Calculate the small signal voltage gain. Right? Very simple. Now let us begin. This is a new voltage. We do not know what is the value. Let us call it as X. Right? First, now we need to find what are the variables that we have. VGS, VT, VDS is all we have to find out. Now let us quickly note down first thing. VGS1 is Vn, right? VGS2 is Vx, correct? Here is VGS. So it is VDD minus Vx. This is the important point. Third, VDS1. VDS1 across M1. So it is Vx. Next, VDS2. What is VDS2? Drop across this. So this is the VDS2. How much is that? VDD minus V out. Next, you have ID. Another value you need is, what is VRD? Right? What is the voltage drop across the resistor? That is V out minus Vx. Okay. So these are the known variables that you have to find. Let's begin the solution. Okay. Can one of you tell me what is the method to follow, or how do we begin the solution here? Okay. Nobody is there. Apply KVL here. Apply Kirchhoff voltage law at mesh. It is not a loop. At mesh created by M2. What will that be? To start off with VGS. Right. So the current flowing through this one will be GM2 VGS1, which is V in is that GM2 GM1. Let me do it a little differently so that you people can follow without jumping into signal. Let us draw the small signal diagram here. Small signal diagram. Now we will have two small signal diagrams. This is one. This is two. This is for the PMOS. This is for NMOS. Okay. gate, drain, source. This will be gate, drain, source. Okay. So this is the gate, drain, source, source. Now let's see how do we connect. V in is connected to the gate here. So this is V in connected to the gate. Same applies here. Then GM VGS, GM V in. And there is R out. Right. Next, gate. What is connected to the source? Ground. So this is grounded. Power supply is there. Now there is gate connected to the VX. So gate is connected to VX. This is plus minus. Okay. Then GM VGS, GM VX, GM2. Note the current, it is going upwards, right? Need to connect it up. This is RO02. Going to the ground. Here it is your drain current. Now, between the V out, where is the V out? V out is drain of this circuit. So this is your V out. Between V out and the drain of this circuit, there is RD. So RD comes here. Okay. Now that you have got here. Now what are the mesh supply that you have? What are all the equivalent values? We need to find out what is Vx. So find out what is Vx. Current here, right? How do you find out what is the current? This is one loop that you have. What is that? GM2 Vx plus V out RO2. V out by RO2. GM VGX plus V out by RO2. Then do we have any other mesh here? No. This is the current flowing upwards. This is the current flowing outwards. There's a current flowing inwards. So this will be ID in this branch. So this is total ID. This is ID flowing one branch here, ID flowing another branch here. Let me call this current that is flowing here, the same resist current that is flowing through RD. So your ID is to come out and flow like this. So is equal to ID. Should know. Another equation we get is how do we connect these three there? What is the same current ID that is flowing? The same current ID is equal to GMV in and what is this voltage? Vx plus Vx by RO2, RO1 is equal to ID. Now you equate these two equations. So what will that become? GM1 V in plus Vx by RO0 1 okay. ID has got one more factor here, right? So there is another voltage here. So you will get one more mesh here, which is these two currents will be same as here. So another voltage equation will be if you apply KVL mesh here. So V out minus IDRD minus Vx is equal to 0. Correct? This voltage is Vx. Right? Drain of this value. So V out is IDRD plus Vx. This is one equation. Or Vx is equal to V out minus IDRD. This ID is given as sum of GM/VGS plus VAV or not. So this will be equal to V out minus ID is GM V in plus Vx by R naught. Again, I do not want to bring in Vx. Let me do it some other way. Okay, let me complete this equation. When you apply the KVL, when you apply this KVL, the value what you get is GM1 V in GM1 V in plus this is GM1 is current and is Vx by R01. GM1 V in plus Vx by R01. So this is the total amount of current. That multiplied by RD is the current into RD is voltage plus Vx is equal to V out. So this is the same equation. Vx V out minus IDRD is given here. So this is one equation. Second one. Finally, what you do is you apply KCL. Where do you apply KCL? Apply KCL at Vx. What do you get? Is the current, right? Minus GM2 Vx GM2 Vx, this current plus V naught R naught V out by RO2. Whole thing negative because current is going in the opposite direction. So that will be negative is equal to what is the currents that are getting here? These two are the current that is flowing. GM1 VN plus V out by Vx by R01. Now let us copy these two equations and simplify. This is one equation. This is the second equation. Now let us find a way to remove Vx from this equation. First thing. This is equation 1 from KVL. Sorry, equation 2 from KVL. This is equation 3 from KCL. Okay. Now utilizing 2 and 3, we will simplify. This gives you Vx is equal to 1 plus RD by RO1 is equal to V out minus GM1 V in RD. GMVGS into RD. This is one equation. Here this becomes Vx 1 over RO1 when it comes this side plus GM2 is equal to minus V out by RO2 minus GM1 Vn. So what is the Vx value that you get? Vx is equal to minus of. So we will write this way: GM1 Vn plus V out by RO2, the numerator, whole divided by GM2 plus 1 over R1. So this is Vx value. Now we can substitute this equation in 1. So what does this give? We will use 4 into, that becomes GM1 V in 1 RD. GM1 V in RD plus RD by R0, right? Px times 1 plus RD by RO1 Vx equal to V out. Now this, when you substitute here, GM1 V in RD plus 1 plus RD by R0 1 times minus, right? So negative. So become minus. Vx we will substitute with GM1 V in plus V out by RO2 over GM2 plus 1 over RO1 is equal to V0. Now, if you do see here, this term multiplied by this term multiplied by plus this term will give you V in factor. This multiplier times V out by R2, when it goes the other side, you get V out. So let us substitute that back. GM1 RD minus 1 plus RD by RO1 multiplied by GM1 by GM2 plus 1 over RO1. Entire thing is multiplied by V is equal to this minus. If you go to the other side for V0, you'll have V out, whole in bracket 1 plus this factor. What is this factor? V8 by RO2. V out by RO2 divided by GM2 plus 1 over RO1. This multiplied by this factor 1 plus RD by RO1. If you subtract, if you divide these two, you get AV. V out by V in is equal to 1 plus, sorry, this V out will not be 1 over R2. 1 over R02 divided by GM2 plus 1 over R01 whole multiplied by 1 plus RD by R01. This whole value divided by this entire value will give you your Vn. Now, if you really want to find out the exact substitution, you can do it as your next task. Let me give you a closed form expression. I have solved this earlier, so that will be given as AV is equal to V out by V in. That's equal to GM1 times, you see here, this GM1 times GM2 RD minus 1. GM2 RD minus 1 whole over GM2 plus 1 over R01 plus 1 over R02 over 1 plus RD by R01. So this will be your gain. Now, if you see, this is happens the dependence when you add cascode devices, add a resistor in between, add feedback. So what is your takeaway? What are the takeaways here? If there is RD coming into the picture between the drain of one PMOS device and the drain of the other, if there is in a feedback loop, you will see that the RD helps in reducing the gain, but it also increases the bandwidth. So GM2 RD increases the bandwidth, but it is reduces the gain. So we will, if you multiply is a feedback, if you take, this will be your gain and bandwidth factor, and this will result in your linearity. By reducing your gain, you will reduce your linearity also considerably. So this is one another example. Next, let us introduce a new topic. Any questions now? Next topic, we will do something called a source follower, or it is CD amplifier, common drain amplifier. So before I start, any questions on the common source amplifier till now? No questions? Okay. Now, what is common drain? That means drain is common to both input and output. For example, NMOS device, you give the input at the gate and take the output at the source. Because you have to take an output, you need a load, which could be RS. Here is the output. What is common to the two? VDD. So input is applied at the gate, output is sensed at the source. For practical purposes, can this be treated as a source degeneration? Possible. But now, what is the connection? What is the connection that is needed? To know what is to be treated, let us do first activity here. Find out. What is the input impedance? Input impedance is infinity. Nothing here. What is the output impedance? Output impedance is source degenerated, right? So that will be RS by 1 plus GMRS. We will check. I will keep this open and we will find out. How do we do that? Let us do another thing very commonly that you can notice. So what is VGS? NMOS device. So this is your VGS, G and S. VGS is VG is V in, VS is V out. Right? So VGS is V in minus V out. What is VDS? VDS is VDD minus V out. Now what is V out? V out is ID times RS. So what is VGS? V in minus IDRS. What is VDS? VDD minus IDRS. V out is given here. Now let us do a small signal amplification. Small signal model we will draw. The small signal model can be given as, let us make your things again familiar. Gate, drain, source. Gate, drain, source. So what do you happen here? Gate. At the gate you have V in applied. Plus, minus. At the drain there is nothing here. So drain is connected to the ground. What is source? At this source you have a resistor connected to the ground. RS. Now this is your VGS. What is VGS? This is V1. Here will be GM1 V1. Is there an R note coming? We don't know if R note is coming. What is the other there? Another one you will see is GMB times VBS. What is VBS? This is V1 or source voltage is V out. So VBS is equal to negative, right? Minus V out. Where is the V out taken? Where is the V out taken? V out is taken at the drain value, right? Is V out equal to V1? No. Why? We will understand. First thing we will do is we will apply KVL in this loop. Applying KVL at input. What do you get? V in minus V1 is equal to V out. This is equation 1. Second, we will apply KCL. Where to apply KCL? Where we have current sources. How many current sources are there? There is one current that is flowing here, which is ID, IDRS. Now that is cumulatively flowing through these two devices. So if you apply KCL at this node, KCL at source, or you could apply, say, I will drain. It doesn't impact much. You will get a similar answer. So what will be this be? If you apply KCL here, this current flowing through these two devices, that would be GM1 V1 plus GMB VBS is equal to V out by RS. Now VBS is equal to minus V out, right? So you will get GM1 V1 is equal to V out by 1 plus RS. VBS is minus V out, so it will be minus plus GMB. So there is a relationship between V1 and V out is given. So substitute that here, you will get the answer. Now what will be V in minus, let us simplify this, V out 1 plus RS, 1 over RS plus GMB divided by GM1. So you will get the same thing as V out 1 over RS plus GMB over GM1 is equal to V out. By simplifying, you get AV is equal to V out by V in is equal to, what is V out by V in? This is 1 plus value, right? Now let us see. V out will be one plus 1 by RS plus GMP over GM1, right? P in as another side. So what is this left over as? To take the LCM, 1 plus GMB RS over RS whole over GM. So that will be GM RS, GM1 RS. Now if you further simplify this, you will get apology, this will be 1 over, sorry, 1 over. So this value will be GM1 RS plus GMB RS plus 1 divided by GM1 RS whole inverted. Now that value correctly, if you write, which is GM1 RS divided by, if I take RS common factor, 1 plus GM1 plus GMB times RS, right? So this is GM1 times R0. R0 is output impedance. So that output impedance here, you can write it as RS divided by 1 plus GMRS, if it is not connected, or it will be GM1 plus GMB times RS. So that is simple action. What do you note here? There is no sign here. So this is non-inverting amplifier. This is a non-inverting amplifier. Okay. So this is how we will get. Let us see. What are the observations that you have? Okay. we will have what are the observations that are present. AV is equal to GM RS divided by 1 plus GM plus GMB RS. So in this case, what will be your observation that you get? First one, if your V in equals VT, Vn is equal to VT, VGS minus VT will be 0. So your GM will be 0. Therefore, AV will be 0. Second, as V in increases, will increase, and ID increases, GM will increase, and as GM increases, AV will increase. So what is the maximum factor that you will get? The RS will become effectively GM plus GMB times RS will be extremely large. So you will effectively get the ratio AV is equal to GM by GM plus GMB. Now we have defined eta is GMB by GM. So this equation will now become AV equal to 1 by 1 over eta. So this is another factor. Now what does this factor mean? That as eta decreases, 1 plus this decrease value change. So this leads to increase in AV. And as AV is increased, but how much will it increase? It will not go much. So therefore, you will see AV typically will be less than V1. Let me write that clearly. As eta decreases, there is increase in AV. But typically eta is of the value of 0.2. So when eta is 1 plus 0.2, sorry, eta is 0.2, gain becomes 1 over 1.2. So your AV is typically less than 1. Now, in case there is an infinite RS, even if there is infinite RS or it is open circuited, the gain is still going to be less than 1. Somebody had a doubt? Anybody had a doubt? No. Now, next we will try and find out what happens if small signal output impedance comes into the picture. But we have found out that what is the impact of channel length modulation. What happens when channel length modulation is present in the circuit? First thing, in the circuit, as the body is not connected to the ground, there is a finite effect, and that finite effect shows body effect. And with the body effect, we have found out that your typical R out is directly proportional to 1 over GM plus GMB. Okay, body effect reduces your output impedance. Now, what happens if you take into consideration channel length modulation? If you introduce channel length modulation, you will get R out here. You will get R out here. So the moment this R out comes, GM plus GMB which is there will have a parallel device. So intuitively, channel length modulation, because it is giving a parallel device, the effective R out will be 1 over GM plus GMB parallel with R out. So this is the impact that you have along with channel length modulation. Now, what does this kind of a source follower? Now here, why is this called a source follower? I had written down beginning. So whatever is applied at the gate is followed here. So what does that mean? This topology will see that whatever is present at the gate will appear at the output with a BT device. So if you need the source to follow something, the source will follow the gate. So you will see the source follower coming into the picture. Another is you will have a high input impedance here and low output impedance. So this can act also like a buffer, right? If you want to have an impedance transformation, you can use it with impedance and output. Another thing that you can use is the common feedback that you will get is AV, voltage gain is typically 1. So you will not see much voltage gain here. So that is why it is called as a buffer. Since you can, the unity gain will allow you to work as a buffer. Now there are two factors that you have to consider. Since there is this GMB factor and the CLM factor here, you will see that it is a noisy circuit, right? First thing is it is noisy. Second, it is not suitable for low noise applications. Right? You should not use this for low noise application as more gain is there. And another thing with this one is here it is a non-linear circuit, right? Because you have body effect and channel length modulation impacted. So the gain is also not impacted by GM. We saw that a very high value, your gain will be GM by GM over GMB. So as this varies, it is a non-linear circuit. So the common drain amplifier will be in this way. Now, since your mind is fresh, let us do a quick comparison. Comparison between common source and common drain amplifiers. So how does that look? Your common source looks like RD, V out, V in. V in at the gate, R at the drain. Now what about your common source amplifier? VD. This will be the last topic for the day. I will let you go a little early so that you can have your dinner a little early. So this is your I. We will have a resistor here to tap the load R. Sorry, this will be RL and you will get the R out value here. Now, what is the first thing we will find out? What is the gain? Gain AV is given as minus GM RL. What is the gain given here as? This gain will be given as RL, GM by GM we did, RL by RL plus 1 over GM. Okay, this is inverting. This is non-inverting. Lastly, this provides a higher gain, right? higher gain, and here AV is approximately equal to 1. So these are the 3 feedbacks that you will have to work with. Take away. Understand this takeaway and take it forward. Okay, I will end the class here today. So may I request you all to come online for the customary photograph. Can you turn on your videos, please? So I will give the assignment questions. I will post it tonight and you can have a look at it. We will thank you, everyone. See you all on Saturday. Have a good evening.